averaging 2 degree of freedom system. It has an element of the 2 to 1 parametric resonance that we have seen before. It is a simple mechanical system. It is idealized, and so it has some interesting behavior as well. Okay, so after all these promises, here is a mass m. Its displacement is measured from some inertial location. There is a spring here connecting it to another mass. This one has a spring as well as a dash part connecting it to ground. This displacement, well, let me correct that. It's from here. This displacement is x1 and this displacement is x2. The free length is L0. This is a mass m. This mass could be different, but I am giving it the same value. This spring stiffness is K. This could be different, but I am giving it 4K. I could detune it a bit, but I am not doing that. So there are nearby systems with other parameters. I just want to keep it simple. This dash part is C, and on this mass there is a force which acts, which is F sine 2t. So I could have detuned it, but I am not doing that. You will notice that if this mass does not move, no movement, then purely vertical motion is possible over here. This is resonant forcing. There is no damping here. This is resonant, and there is no damping here. That's an idealization. In the presence of no damping, this amplitude will get bigger and bigger and bigger, and eventually this will become unstable. And so then this will oscillate and this amplitude will go down, and we will see that dynamics. Okay, so now let us think of equations of motion for it. And what we do is we say this point has come down by x2, and this point has gone to the right by x1, and the free length of the spring was L0. The new length is equal to the square root of L0 minus x2 square plus x1 square. The tension in the spring is equal to 4K L0 minus L, L minus L0. That's the tension. And let's see, that has a component. So this tensile force which acts on this mass has a vertical and a horizontal component. This component is T x1 over L. You see, that's the component, because I want this angle, that length is L, this length is L. I hope that's clear. Okay. Similarly, over here there is similarly a tension, the same T. There is a vertical component and a horizontal component. The vertical component is of interest, and that is equal to T times L0 minus x2 over L. Okay, good. With that, we have our equations of motion, and so I have m x2 double dot is equal to f sine 2t plus t L0 minus x2 over L. This is one equation. Remember that this L is a complicated function of x1 and x2, so this is a nonlinear system. Now I have another equation. This is based on, if you like, it's based on a free body diagram. There is F here, there is a reaction here, and there is a tension here, and I am resolving the vertical component of the tension. So this is the free body diagram that is attached to this equation. There is another free body diagram here on which there is a tension in this direction. There is no applied force. There is some other reaction over here, N, which we will get rid of. There is a force here which is Kx1, and there is another force here which is Cx1 dot, and therefore, because this mass is also the same, I have mx1 double dot plus equals minus, let's see now, this is minus and this is minus, okay, because x1 is taken positive, minus k x1 minus c x1 dot. This is taken as tensile, so in this component, so it's minus t x1 over L. So that's the other equation. I'm sorry for the hesitation there, you can check, those are the equations. Okay, let me now show you in MATLAB this int. This int is there for a reason. Let me quickly show you what that reason is. If you linearize this system, let me do that here. Linearize system if, then what happens is, this is 4k, this is m, this is k, forget the damping. There is one mode where this vibrates and this does not, no movement, and the natural frequency is square root of k over m times 2. There is another mode marked in yellow where this moves and this does not move, no movement. And in this case the natural frequency is square root of k over m. So the ratio is an integer, it is 2:1. Okay, such a simple rational ratio between two natural frequencies of two modes the existence of such a simple ratio is called an internal resonance. Could be 1:3, could be 3:2 or something as well. That is why I have called this MATLAB file int for internal resonance. I have chosen the force and damping to be very small for reasons that will be clear to you later. There is an interesting behavior here. By choosing units of mass, I have made the mass 1. By choosing units of length, I have made L0 equal to 1. By choosing units of time, I have chosen this k to be 1. I can do that. There is no real problem. You can think of these as non-dimensional now. Now I have x is q1, x2 is q2, x1 and x2, v1 and v2. That is my state vector. Here is L. This matches what I had written earlier. Here is the tension. That matches what I had written earlier. V2 dot is T L0 minus x2 by L plus f sine 2t by m. Let's see if that's what I have here. T L0 minus x2 by L and so on. So that matches. And then over here minus kx1 minus cv1 minus tx1 L by m. Okay, so that's v1 dot. This is my equation of motion. The first thing to show you is a numerical solution. Okay, so what I will do is I will say q0 is equal to rand 41 by 10. I'll use a small initial condition. Okay, then what I will do is I will say tq equals, now there's a lot of other stuff here, let me not do that. Let me say tq equals ODE 45 to mass int. Let me, since the forcing is sine 2t, I will use an integer number, so I'll say 0, 300 times pi something, and then I will give it this initial condition from OP. Okay, very good. Now let me plot just x1 and x2. That's the answer. You can see that after some transient it is settling into some kind of periodically modulated state, right? So this, the first one is x1. You can see that its frequency is small. You see over here. You can see that the frequency of the red one, which is x2, is twice that of x1. You can see that the amplitude is modulated. It slowly changes. I could run it longer and you would see that the amplitude settles to this value. So you can see it's about 0.04 here for the blue one. Okay, so let us see if with the same initial conditions, let me run it longer, 600 pi. And you can see that it has settled to a periodic state. This periodic state may or may not be unique. We will study that later. But over here you can see that the amplitude is about 0.04 and this is about 0.02. The amplitude for x2 is 0.02. The amplitude for x1 is 0.04. x1 has a frequency that is essentially sine t and x2 is essentially sine 2t. Okay, very good. Let me now take a different initial condition. Let me call this q1 and let me make this maybe 2, slightly larger initial condition, and let me run this one with the initial condition q1 and let me plot that, and you will see that it has settled to apparently a different solution, and we can go in there and look. It's periodic also, but now it is definitely not 0.04. It is more like 0.05, and the red amplitude which is the amplitude of x2, is also significantly more than 0.02. It's something else. Parameters have not changed, and you can see once again that the blue one has a frequency that is double that of the red one. Okay, so the modulation has some different dynamics over here. This is the steady state. There is an initial transient when some things decay, but after that we have this phenomena here. It is also qualitatively interesting for you to think about what happens. What happens here is that this is the blue, the red is x2. x2 amplitude is slowly increasing almost linearly because it is a resonant interaction. It doesn't have damping. But then x1 becomes unstable, and when x1 grows, it grows at the expense of x2. So the amplitude of x2 goes down. When it is down, then x1 is no longer unstable, so that comes down, and this is the interaction that goes on. However, there does not seem to be a single unique behavior. Okay, so this is another solution that we have got. You can see it is different from the first one. This maximum is about 0.05. Okay, very good. Let's come here now and try a third initial condition, and this one we will use an even bigger initial value. This is a numerical exploration of our system. And you see that, oh, I forgot to change the initial condition, I'm sorry. That's why it looked exactly the same as before, but I have changed my initial condition now. Okay, let us see how that has worked out. It has again settled to something that is approximately periodic. This one again looks like it is about 0.05, so that is not very different. Let me try something else. Q2, let me try rand n. Okay, how about times 3? Okay, so here what has happened is x2 has gone over to the other side, okay, because of the initial condition being what it is. If you look here, you see this mass. If this initial movement is a bit large, this mass can go over to the other side, and then this will be like this. So that is a possibility, and since L0 is equal to 1, then x2 would have a mean. x2 would have a mean of about 2. Okay, so this is what we are seeing here in this solution, but we will not be interested in this. I just wanted to show you that it exists. So the mean is around 2. Okay, but we will not be interested in such solutions. Let's come back and try one or two more. In fact, I have them loaded somewhere. Let's try that loaded solution with Q2. That is some initial condition. Okay, so once again about 0.04, then I want the other one. I'm wasting time here, but you get an idea that it is actually, see, this one is somewhat different. Over here this amplitude is 0.75 or so, and the red one has these two lobes, you know, one linearly increasing part, then x1 becoming unstable. As it grows beyond a point, it starts taking too much energy from x2, so x2 goes down. There is some kind of even dynamics in x2. We have seen this behavior. Okay, now if we look at this behavior a bit carefully, so we see that it is about 0.76. Let me try something. Let me try so I'm going to perturb it a bit. And you see it has come back to some other completely different value. But that was a legitimate solution. Okay, but it has come back to 0.04. Here smaller perturbation. And you see now it was 0.76, right? But now it is 0.07, not 0.076. So there is actually a family of such periodic solutions. I hope you will agree. These maxima are reaching really the same value. Okay, so this is the system we want to understand. It has periodically modulated amplitudes for x1 and x2. Those modulations can be complicated. It seems that we should be able to get something with averaging, and we are going to try averaging now. So let me lower this one, let me lower this one, and come to maple. Alright, so we are writing the equations again. Let me see, maybe I'll just come here. Okay, so here are my parameters. I'm defining to be 1. Here is L as before. Here is the tension. So let me start here. 1, 2, 3, 4. Okay, so then here is the equation. The equation is tension, I'm dividing by the mass. This is x2 double dot. Here is the force from the tension and from the resonant forcing. Okay, so you can see that it's a complicated nonlinear equation. Then here is the second differential equation. That's for x1. And let me stop here, because this is the equation that we have integrated numerically. Now what I will do is I will come here and say, since x1 and x2 are small, maybe I can expand in a multidimensional Taylor series. So this is a linear term, this is a linear term, it is this part that needs to be expanded. I can come here and I can say expand this quantity here in a multidimensional Taylor series with the variables x1 and x2 being small, truncating and removing third order. So I get this equation. I could have said keep up to fourth order, in which case I'll get some cubic term. I could have said keep up to fifth order, and then I'll get still more terms and so on. But I have decided to keep the first nonlinear terms that arise. So here this is linear, this is linear, this is resonant forcing, quadratic. Okay, so that's what I'm using. Now same for the other equation, which is this equation, dE2, same here, and I have a quadratic term. So clearly this equation and this equation are a lot simpler than this equation and this equation. So let us go now and see how they work. If this equation and this equation give you about the same dynamics for small x, then it's a good idea to analytically treat these. Okay, so we go to MATLAB again, and what we do now is 2 mass internal resonance and 2 is second order. So you see these are the same equations. There is that minus 2x1 square for x2 double dot, minus 2x1 square for x2 double dot, and minus 4x2x1, minus 4x2x1 for x1 double dot. Okay, so and the parameters are the same. Okay, m, k and L0 have already been put equal to 1. These are simpler equations. My question is, this 2 mass int second order and 2 mass int full, do they give the same result? Okay, so to do that, what I have to do now is go back and remove this random component. Well, maybe I didn't need to do that, but it's okay. Here we go. So no, what I will do is put subplot 2 1 no, 2 1 1 and say plot TQ 1 to 2. Okay, so there is my solution. This is for the full equations. Okay, then what I will do is I will come here and use the same initial conditions but for the approximated second order equation, and I will put it in the second subplot. I don't expect an exact match, but if the match is good enough, we can proceed. And I think the match is good enough. The time period of the modulation is very slightly different, but I think it is clear that the second order equation does a reasonable job. We want to get a glimpse into the dynamics of this system. This approximation seems good enough. Okay, let us do one more. Let us say Q0 is equal to, so I have a Q0, very good. So let's try this Q0 here. And that's the second one. So that's a different one. Okay, we'll try this and see what happens. It may not work so well, but we'll see because there are deviations here. Here's what I will do. I will say Q0 is equal to Q and okay, and then I will do that again. So now I am doing the steady state. Remember that I have gone through an integer number of forcing periods. So I've gone here now. I'm still looking at this one. Okay, this is the one to look at. Now I will compare same initial condition, full equations. This is the second order equations. Very good. So I'll come here and I will remove this 2. So this is the full equations. And I will do subplot 2 1 1. And I think that the match is reasonable. I hope you will agree. I can make it bigger for you to see. And you know, this maximum little less than 0.05, about the same. The periodicity little bit different, but not too different. Okay, so so now the second order equations are good. Fine. Now I come here, I'm going to do averaging for the second order equations. Before that, I have to figure out what is small and what is big. If I say x is order epsilon, this is epsilon, this is epsilon. This one, epsilon square, is going to give me some epsilon. Okay, so that's one issue. Now I come here, let's see now. Here, this is epsilon already, this is epsilon already, this is epsilon already, and this is epsilon square. Okay, so after I divide by epsilon, this will be order epsilon. After I divide here by epsilon, this will be order epsilon. And so over here I want this to be order epsilon also. That means f must originally be order epsilon square. Okay, while over here when I divide by epsilon, I'll divide by an epsilon here, and then this must originally be order epsilon. This must be order epsilon square. This is why I had chosen these parameters, you see, because this c is approximately 33 times smaller than 1, and this f is approximately 30 times smaller than c. So if I take c to be 0.9, right, so 0.9 by 30 is 0.03, and that by 30 is this. So f is 0.9 epsilon square, c is 0.9 epsilon. Okay, when I do that, f and c are still being retained as parameters, but over here, from here I have come to this equation. Now there is an epsilon here and an epsilon here. and I've come to this equation, there is an epsilon here and an epsilon here. These are my two equations. Okay, now when I put epsilon equal to 0, what do I get? I have x2 double dot plus 4x2 equals 0. That means x2 is a sine 2t plus b cos 2t. That is why I am coming here and saying x2 solution a sine 2t b cos 2t, and x2 dot solution is the derivative of that, okay, time derivative of that. So this is my transformation for x2. Similarly, I will come here and I'll have x1. When I look at the x1 equation, there is the harmonic oscillator. This is the small perturbation. So the solution is a sine t plus b cos t, or p sine t plus q cos t. That is why I have this over here. Okay. Now what happens is, as we have done before, if this is x2, then its derivative has a dot sine 2t plus b dot cos 2t plus 2a cos whatever, something, those equals that. So that is what leads us to this equation. Okay, so if I take x1 as differentiate with respect to p, multiply by p dot and so on, this thing has to be 0. That's one equation. That didn't work for some reason. And this thing has to be 0 is another parallel equation for the other variable. Okay, now this font I can't quite control, but it's all right. Similarly, when I take the x1 dot solution and take its derivatives, then the true complete derivative is this, of course. So I take that and substitute that expression into x1 double dot. In place of x1 dot, I substitute whatever I have. In place of x1, I substitute x1s, what I have, and so on. And then that is my equation 3. And similarly, I do equation 4. So first I take the derivative of x2 dot solution and then substitute into E1, which is the x2 equation. And I have that solution. Then what I do is I solve EQ1, 2, 3 and 4 for A dot, B dot, P dot and Q dot. Very good. When I do that, you see A dot is epsilon times a bunch of things. Where is B dot now? Up to here. All of that is epsilon. Then there is B dot and that's order epsilon. Then there is P dot and that's order epsilon. And somewhere there is a Q dot and that's order epsilon. Okay, this is in Lagrange standard form. Then I will do my averaging. So what I will do is I will substitute that into the expression A dot. There are higher order terms, but it's basically 2 pi is an acceptable period for it. So I'll integrate to 2 pi, divide by 2 pi. This is A dot. Okay. Very good. This is B dot. Similarly, this is P dot. That's Q dot. Now, after we have averaged, you see I can set epsilon to be any number and it just stretches the time scale. So I will just set epsilon equal to 2 to get rid of these things. This square bracket over here in this list is important. The square bracket makes it a list. When I have curly brackets, that is a set. So it may give it in a different sequence. Okay. But this will give it in the same sequence. So I substitute epsilon equals 2. This is my averaged equation. Okay, A dot, B dot, P dot and Q dot. Okay, let's go to MATLAB and you will see I have now this averaged equation. There it is. Okay, Q dot. I've put F equals 0.9, C equals 0.9 because that epsilon has gone away. Now this was the value. Now in terms of putting epsilon equals 2 here, I'm just changing the time. Those numbers don't change. If you think about it, it should be clear. Here is the slow flow. Okay, very good. So now what I'm going to do is I'll show you that these averaged equations have very similar dynamics. So let's see, now this will be 2 mass average. This has to be a lot less. Okay, so it is more like 10 pi because we have factored out the epsilon. Okay, right. So here we go. This is some random initial condition. This initial condition does not match that initial condition. Okay, so there's a problem here. Let's see what the problem is. Two mass, AVG, nothing, no real problem. Now you must remember that I have amplitudes. So A and B together determine the amplitude of x2. Not here. Here. A and B together determine the amplitude of x2. P and Q together determine the amplitude of q2 and of x1, and so I will have t, and then I'll have square root, and then I will have q1 square plus q2 square. This is the amplitude of x2, and then t, and then a similar thing but with 3 and 4. And you see that we have, this is big now. That is because I have to multiply by epsilon. Remember, epsilon was 1 by 30. I forgot to do that, so I'll do that here now. Once again, epsilon is actually 1 by 30. It is only to make the integration run faster that over here, that epsilon by 2, I just removed it. Okay, so I hope you're not confused about that. But this is the actual amplitude that we are interested in, and you can see it is fairly similar to what we had. It is a bit big. There are initial conditions for that which will give you similar solutions. I can come here and now start with some other initial conditions. So you can see it is some other solution like that. Let's start with still other small solutions. What am I doing here? No problem. This is fine. Let me start with 30. Make this a bit smaller, make this a bit, each of those is coming out to be fairly big there. Let me try all positive. I know this is looking like all of them are just giving the same answer. Let me show you first that they are not. So I'll put hold on, and then I will try, and this one will be plotted in black, and you see that it is actually a different answer. It is settling to a different value there. Okay, it is not the same solution. They are all turning out to be slightly big amplitude solutions, but I promise you there are other solutions for this, which if we find the right ones, they will work. Okay, so let me try to look at this equation here. when I look at this equation, if I look for an equilibrium, p square is equal to q square. Okay, now if if a dot is to be 0, p square has to be equal to q square. F is 0.9. Let us think of it loosely as 1. In that case, this is half, goes over to the other side. P and Q have the same magnitude, but it is clear that PQ is negative. That means P and Q are of opposite sign. Each magnitude is roughly 1 by root 2. And then you come here, and if you look at this, I have done this before, so I know if I make in this one, once I have solved for P and Q from here, so once I put it here, these are linear equations in A and B, so they have a linear unique solution. But what happens is, if you put A equals 0, then by direct substitution you will see that the two equations you can solve for B works out to be something, half or something. Why? Because A is 0, P is the opposite of Q in sign, P goes to the other side, that's plus but same magnitude, and then B becomes half if C is about 1. Okay, so when I come back here, I can try an initial condition of the form 0 minus 0.5, 0.7 minus 0.7. Okay, let me try that initial condition. This one I will plot with green, and this first one I will plot with magenta. Okay, you see here, so these are one of those more slowly oscillating solutions that we had seen before. Okay, here this one, and this one are quite different from this one. They are all solutions of the same system. Okay, now let's do one more. Let's do Q0 is equal to Q0 plus rand n 41 by 30. So I perturbed it a bit. Well, that didn't change too much. Maybe I'll perturb it a little more. Okay, so now let's go there and look. We have to get a bit close to understand that these are in fact different solutions, but when we get close, you see that the maximum amplitudes are different. Okay, so they are different. Let's do one more. Let me plot this with dots. So we will know that that's the new one, and you can see that this has a completely different character again. So all of those solutions are possible. Our physical interpretation of this system is that damping in the X2 system is necessary to give it a well-defined behavior. But in the absence of X2, we can actually simulate this system. Equations I have shown you, you can simulate them, and if you match initial conditions better, you will find that there is actually a pretty good correspondence between the original solutions to the original full equations, solutions to the equations truncated at second order, and solutions obtained by solving the first order averaged slow flow using very routine method of averaging. One, you may say, if I am solving it numerically, what is the use of doing it? Well, you see, this does not have a sine omega t and a cos omega t. The numerical integration proceeds much faster. I can, I am integrating over a shorter period of time, getting the result almost instantly, right? So I'm getting the result almost instantly, right? While over here, when I was doing this, let us say with 600, and then, right, so it was taking quite a bit longer, for example, quite a bit longer. So we can actually measure it. MATLAB has a nice command. So that took about 2.2 seconds for the original full equations, while corresponding integration here is just much smaller, right? So it's about 50 times smaller. Now that's one thing, but also the other thing is there are situations where you will be studying these in greater detail and trying to find equilibrium points and things like that. You will find stability results, which from the original much harder to find. So the averaged equation is partly it's interesting academically, I think it's pretty. Partly it gives you insight in some cases. It lets you obtain equations that you can, even if you numerically integrate them, to proceed much faster. And this example in particular was intended to be a demonstration of averaging for a 2 degree of freedom system. Thank you.